Hello everyone. In this tutorial we will discuss some problems relating to the content of module 9 and 10. So, we will try to solve about 3 or 4 problems, and we will also upload an exercise which will consist of about 9 to 10 problems which you can solve for yourself. So, going to the first problem, which is as follows. Given a state space model with the following matrices A 1 0 0 0 0 minus 2 1 0 1 0 minus 1 0 0 0 0 minus 3. So, this is a state matrix, and then the input matrix is 1 1 0 0, which means there is a single input, and the output matrix C is given by 0 0 1 1 and D we take it to be 0. So, given this system, we are asked to find a minimal realization. So, what is a realization? We saw that if any system is represented in this manner A, B, C, D matrices, then it is called one of the realizations, and we have seen that any system which can be realized from a transfer function, it will have infinite possible realizations. So, one realization is already given to us, and using this realization we are asked to find out another realization which is minimal. So, even minimal realizations there could be many, we are asked to find one of them. Now, how can we go about this? First, we need to check if the system is fully controllable and observable. So, once we check this, we arrive at 4 cases. The case 1 being the system being fully controllable and observable. The second one being the system being controllable but not fully observable. The third one being the system being observable but not fully controllable. The fourth one being system being neither fully controllable nor observable. So, in the lectures we have seen that when the system is fully observable and controllable, then the given realization is a minimum realization, because we know that the minimal realization always is in fully controllable and observable form. But in the cases when the system is not fully controllable or not fully observable, or neither of them is being satisfied, then we need to find a lower order system which is minimal. So, now when the system is not fully observable but it is controllable, then simple way of finding minimal realization is given by the observable decomposition. So, you just take a system decompose it into observable and unobservable parts, then the observable part will be the minimal realization. So, in this case, when the system is not fully controllable, then the minimal realization is given by the controllable decomposition. So, now what if happens that the system is neither fully observable nor fully controllable? Then minimal realization is given by, you can do this in two ways. One is using Kalman decomposition, but finding the basis for a Kalman decomposition is very difficult. So, we have an alternate way of doing controllable decomposition plus observable decomposition. So, we will do one after the other. So, if we take this system, this is the given system is neither fully controllable nor fully observable. You can check this using the controllability and observability matrices. The rank of those matrices will tell you that this system is neither fully controllable nor observable. Now, so we either need to find the Kalman decomposition, or we have to do first a controllable decomposition and then an observable decomposition. So, as the system is a fourth order system, instead of doing this manually, we will try to solve this using MATLAB. So, in this case, I have written a code which will give you the minimal realization of any given state space model. So, the first part of the code loads the model, and then we are finding out the controllability and observability matrices using these commands CTRB and OBSV, and then we check the ranks. So, now the code goes as like this: if both the ranks are full, then we know that the system is fully controllable and observable, hence the realization is given to be minimal. But what if the controllability matrix rank is full but not the observability rank? So, in this case we follow the observable decomposition. So, this is what we are doing. To find the observable decomposition, we take the SPD of the observability matrix and then use the eigenvectors in V as the model matrix for transformation, and we do the following transformation and then we get this. So, now the system is in minimal form because we already know that it is fully controllable. What if it is otherwise? The system is fully controllable, fully observable but not controllable. Then we do the reverse. We find the SPD of the controllability matrix, then using U we transform the system into a form which will give us the controllable observable system, which is minimal in nature. So, but our case is the third case where it is not fully observable and not fully controllable. In this case, what we will first do is we will take the controllable decomposition and then we transform it into a controllable form. We will take the controllability part and then we will take an observable decomposition on the fully controllable system. So, this is what we do, and if the rank is less than the full rank, then again we do Again we find out the observability matrix, then we take the SVD of the observability matrix and then transform as follows. So, this code will run the whole thing. I already copied the whole model into this variable called ss underscore model. So, I will run this code and you will see what happens. So, as you can see, the system is neither fully controllable not observable, and we will do a Kalman decomposition. So, which is alternately done using first the controllable decomposition and then the observable decomposition, and after doing that the minimal realization is given by these matrices. So, I will upload this code, you can try it out on different matrices, and so this is the way to understand how minimal decomposition is done. You can also use a command called minreal. So, there is a MATLAB command minreal, which will also give you the minimal realization, but it might not be the same as what you obtained using this way, but you can still verify that both the minimal realizations will lead you to the same transfer function. So, I will leave that for you as an exercise. So, going into the second problem. In the second problem, we are asked to find the controllable and uncontrollable eigenvalues, which are nothing but the poles of the following system. X dot is equals to this is the A matrix, Ax plus B is 1 1 times U, that is a single input. And then after finding out the controllable and uncontrollable eigenvalues, using state feedback, K, the controllable eigenvalue can be shifted to a location or to a value p, and we are asked to find a formula for p in terms of k1 and k2. These are the variables. So, k is k1, k2. So, it is already said that there exists a controllable and uncontrollable eigenvalues. So, we can always find one pole to be controllable and other pole to be uncontrollable. So, how can we find out? So, a simple way is to actually find out the controllable decomposition of this system. So, you can always find out the matrix. Okay, I will find out the controllability matrix. You can just verify, it will be minus 1 1 and minus 2 minus 2. So, its rank is 1. So, I will take a model matrix P, it consists of the first column from here and another column which is linearly independent to the first one, it could be 1 0. So, now using this I will find out A bar is equals to P inverse A P, and if I do that I will get minus 2 1 0 1, and similarly B is equals to P inverse B, sorry, B bar as P inverse B, and this I will get it to be 1 0. So, the transformed system is A bar x plus B bar u. So, now you can see that only the first state is controllable, which means the first eigenvalue is controllable, while the second eigenvalue is not controllable. Sorry, this is minus 1. So, what are the eigenvalues? What the first eigenvalue and second eigenvalue are clearly minus 2 and minus 1, because this is a upper triangular matrix. I can always write the diagonal matrix diagonal elements as the eigenvalues. So, now the first eigenvalue is controllable because 1 is present in u in the first element in B bar, and the second eigenvalue is not controllable. So, now how can we find out a formula for P in terms of k1 and k2 to control this eigenvalue minus 2. So, minus 2 is the controllable eigenvalue or the pole, minus 1 is the uncontrollable eigenvalue. So, which means that I can always change minus 2, but minus 1 always remains to be a pole of this system that cannot be controlled. Okay. So, now we will take this k is equals to k1 k2, and using state feedback I will find out the characteristic matrix of the system with state feedback. I can say it A minus B k. So, if you find out the characteristic equation of the system, it will turn out to be like this: s square plus s into k 1 plus k 2 plus 3 plus k 1 plus k 2 plus 2. So, you can just substitute A, B and k and find out this characteristic equation. Now, if you observe, this can be written as follows: s plus 1 into s plus k 1 plus k 2 plus 2. Now, you can see that the original characteristic equation S I minus A will be s plus 1 into s plus 2, because minus 1 and minus 2 are the eigenvalues. Now, once I introduce state feedback, this s plus 1 still remains, but s plus 2 gets replaced by s plus k 1 plus k 2 plus 2, which means that now I can change my values or choose my values k 1 and k 2 such that I can place this minus 2 anywhere else I want. So, the formula for P will be k 1 plus k 2 plus 2. So, this is how you solve this problem. Now, going into the next problem. So, this problem pertains to the 10th module. It is about observer design. So, this is how the problem goes. So, in this problem we are asked to design an observer, which means we need to find an observer gain matrix K such that we have a system x dot is equals to A x and y is equals to C x, and we want to place the eigenvalues of the observer A minus K C such that they are the roots of this polynomial s square plus d 1 s plus d naught. So, this is the desired characteristic equation. So, this is very similar to the controller design that we did in the previous module. So, how do we go about it? So, as per the dimensions, k needs to be a column vector k 1 k 2. So, now what we will do is we will find out the characteristic equation. Which I can write it as now if I will expand this, I will be getting s square plus s into 2 plus k 2 plus 2 plus k 1. So, we have a characteristic equation coming from A, K and C, and now if we compare it with this given characteristic equation, then we can simply say that d 1 is equals to 2 plus k 2, d 2 is also 2 plus d 2 is 2 plus k 1, which implies that k 1 is equals to, sorry, not d 2, this is d naught. So, k 1 is equals to d naught minus 2 and k 2 is equals to d 1 minus 2. So, this is how we can place the eigenvalues or the poles of the observer system such that they are equal to the roots of this given polynomial. So, this brings us to the end of this tutorial. As I said at the beginning of the tutorial, we will be uploading some exercise problems which are somewhat similar to the content that is covered in modules 9 and 10. You can go through them and post any queries in the forum if you have. Thank you.